We are now going to begin the serious study of continuity. Our approach will be through what is known as topology. Continuity of a function between metric spaces is completely characterized by open sets. So we pause and first define what the topology in a metric space is. So definition, let X be a metric space, then the topology generated by X is the collection tau of all open sets in X. So you take each and every open set and shove it all in this collection and you get this topology, typically denoted by tau. Now I'm going to prove a very basic property about the topology associated to a metric space, and this proposition is rather simple to prove, and you have seen a very similar proposition in the context of real numbers. Proposition, let X be a metric space, then the topology generated by X tau satisfies the following properties. Number 1, the empty set and the whole space X are elements of tau. So this is a natural property that follows immediately actually. Number 2, any arbitrary union of open sets is open. And number 3, any finite intersection of open sets is open. You have seen all these properties in the context of the metric space R, and the proofs are more or less exactly the same. So again, I'm going to be very brief. Proof. Part 1 is utterly trivial, so I'm not even going to bother proving it. Let G lambda be a collection of open sets. Suppose X is an element of the union over lambda G lambda. Okay, then X is an element of some G lambda naught. It has to be at least in one of the G lambda naughts. Therefore, we can find some ball BXR which is fully contained in G lambda naught, which is fully contained in union G lambda. Okay, therefore X is an interior point of the union over lambda G lambda. Okay, that was rather easy. The intersection case is equally easy. Suppose G1 ... Gn are open and X is an element of the intersection of Gi, I running from 1 to n, then we can find R1 to Rn all greater than 0 such that Bxri is a subset of Gi. This is just because each gi is open, therefore each x is an interior point of gi, and hence we can find some ball of positive radius centered at x which is fully contained in gi. Consequently, if R is the minimum of R1 to Rn, then R is greater than 0 and Bxr is a subset of Gi for all I running from 1 to n. Hence Bxr is a subset of the intersection of Gi, and intersection of Gi is open. Very easy proofs. Rather, these are proofs which are sort of automatic. You just start writing down what is it that you must prove and the proof just falls into place. Okay, you have an analogous result for closed sets. I leave it to you to think about closed sets and what you can say about unions and intersections of closed sets. Now let me move to the next page because we are going to introduce the notion of continuity. As usual, instead of just, we have already seen the definition, we are going to now characterize it just like what we did in R in several ways, this notion of continuity. One key change is that our focus will now be primarily on open sets. So we have this theorem, and this is a rather important theorem because it will help you understand the notion of continuity in multiple ways. So characterization of continuity. So the setting is as follows. Let xd and yd prime be metric spaces, and f from x to y is a map, then the following are all equivalent. I am going to use the abbreviation TAFI. The following are all equivalent. F is continuous. Property 2, for each x in x and epsilon greater than 0, there exists delta greater than 0, satisfying, such that dxy less than delta implies dfx fy is less than epsilon. Exactly the same epsilon delta definition that has given us nightmares in when we studied continuity in R. The exact same nightmares are going to now repeat for metric spaces. Only difference between this version of epsilon delta and what you have seen earlier is that the absolute value has been replaced by the distance between x and y. As I have repeatedly emphasized, much of this study of metric spaces would be just taking the definitions and theorems that we have already seen in the chapter on taste of topology, and wherever you see absolute value, just replace it by dxy. Okay, and this is sort of going to illustrate that. Now the next condition we have not really studied in depth when we studied continuity in the real numbers. We had just dealt with it briefly. This is characterizing continuity entirely in terms of topology, and this is going to be very important because it is this equivalent definition of continuity that generalizes to the context of topological spaces. If G subset of Y is open, then the pullback F inverse G is open in X. So of course the first open is in Y, or that's obvious. So you can succinctly say that continuous functions pull back open sets to open sets. Okay, and the fourth condition is just a minor variant of this. If B subset of Y is an open ball, then F inverse B is open in X. So you needn't check that the pullback of every single open set in Y is an open set in X, you need to do this only for open balls. That suffices. So the conditions 3 and 4 characterize for us continuity entirely in terms of open sets, and when you come to the study of topological spaces where you do not have the ability to measure distance between 2 points, and you will also learn that sequences are also not adequate to characterize such things in a topological space, conditions 3 and 4 will save the day. We can characterize continuity entirely in terms of open sets. So on to the proof. Some of the parts will be very familiar to you. The arguments will be very similar to what we have done. Only a little bit of novelty is involved now. So assume f is continuous at x in x. Remember, this means that whenever you have a sequence xn converging to x, the sequence f of xn converges to f of x. This is the definition of continuity we are taking. So fix epsilon greater than 0. Now we are essentially going to show that the sequential definition of continuity automatically implies the epsilon delta version of continuity. Okay. Now suppose the epsilon delta criterion is not satisfied for this epsilon. Okay, I am going to show that this is simply not possible. Given any fixed epsilon, the epsilon delta criterion has to be satisfied. If not, we are going to get a contradiction. What does this mean? This means that no choice of delta works. In other words, 1 by n does not work in the definition of epsilon delta. Does not work in the epsilon delta definition. Okay, I'm sure you can anticipate where this is going. What this means is that given or not given, rather, for each ball b x 1 by n, we can find xn in this ball such that the distance between f of xn and f of x is greater than or equal to epsilon. None of the choices 1 by n work. Note that this bx 1 by n is precisely those points in the metric space X which are at the max 1 by n distance away from the given point X. Okay, so this is just another way of saying that dxxn is less than 1 by n. So the fact that the epsilon delta definition fails simply means that you can find a point xn such that dfxn fx is greater than or equal to epsilon. Okay, but clearly xn converges to x, but f of xn does not converge to f of x. This is a contradiction. Okay, so this shows that the sequential definition of continuity guarantees that the epsilon delta definition will be satisfied. Okay, now we are going to go to the next part. Assume that the epsilon delta definition is satisfied. The epsilon delta definition is satisfied, and even though I state this result as a global one, that is continuity is assumed at all points x, I'm just going to prove it locally. So the proof will actually say a bit more than what the statement is asking us to do, but nevertheless it's useful to have this more general fact, if not in the statement, at least in the proof. So assume that the epsilon delta definition is satisfied at a particular point x in x. Okay, now what I have to do is I have to show that given G subset of Y open, given G subset of Y open, I'm just going to show that F inverse G is also open. That is what we have to show. We have to show that F inverse G is also open. Note that because G is open, we can find some ball. We can find some ball B f of x y, which is contained in sorry, not B f of x y, B f of x r, which is contained in G, which simply because G is an open set in Y. Okay. Now, what we are going to do is to show, rather, I mean, since here I'm not going to show that F inverse G is open, I'm going to show x given G subset of Y open and F of x is in G. This is important. Sorry about that. I missed an important thing. Given G subset of Y open, F of x in G, I'm going to show that x is an interior point of F inverse G. Okay. So I'll be very precise. The statement asks us to prove that whenever you take an open set G in Y, we have to show that F inverse G is open in X. I'm going to prove the much stronger claim that if the epsilon delta definition is satisfied at a particular point X in X, then no matter what open set G you take in Y that contains the point F of X, I am going to show that X is an interior point of F inverse G. In fact, from this, the fact that F inverse G will be open if F were continuous at all points, or rather if F satisfies the epsilon delta definition at all points, is rather obvious, and I'm going to leave it to you. Okay, so coming back, we have this B fxr is contained in G. So what I'm going to show is that F inverse B fxr for which we have this X is obviously an element of this, X is an interior point. I'm going to show that X is an interior point of B fxr. Okay, now this is rather easy. The epsilon delta definition gives us a delta greater than 0 such that F of B xr is fully contained in B f of x r. Here r plays the role of epsilon, that's all. Okay, that means B xr is contained in F inverse B fx r. Okay, this immediately shows that X is an interior point of F inverse B f of x r. Okay, now it's the fact that 2 implies 3 is straightforward now. I want you to think about how, with this stronger fact that whenever you have continuity at a point, you automatically get that X will be an interior point of a inverse image of a ball that contains f of x. So I want you to think about how to prove the full statement 3 from this stronger fact. It's rather easy. Now 3 implies 4 is nothing. 3 implies 4 asks us to show that if whenever G is open, F inverse G is open, we must have whenever B is open, F inverse B is open, where B is a ball. That's nothing. So finally 3 implies 4 is obvious. Now we have to show 4 implies 1. That is, we have to show that whenever we have this condition that when you take a ball, we have F inverse B is open, we'll have to show that if xn converges to x, then f of xn converges to f of x. Okay, so let xn converge to x. Okay, so xn is a sequence in x and x is a point in x, and you have a sequence converging to to the point x, we have to show that f of xn converges to f of x. Okay. Now we already know that so suppose we consider the ball b f of x comma r, then f inverse b f of x r is open. That's the hypothesis. This means we can find delta greater than 0 such that f of b x delta is fully contained in this ball b of f of x r. Okay, so far so good. But because f of bx delta is contained in b f x r and xn converges to x for sufficiently large n, xn is in bx delta, consequently f of xn has to be in b of f of x r, right? Because of the convergence of xn to x, for suitably large n, xn must be in bx delta, but f of bx delta is contained in b of f x r, so f of xn is contained in b f x r. Okay, so this r was arbitrary, and hence f of xn converges to f of x. So the proof again was rather short. So we have shown that 1 implies 2 implies 3 implies 4 implies 1, so all are equivalent. In the exercises I am going to ask you to show some of these equivalences individually, directly showing that 3 is equivalent to 4 and 2 is equivalent to 4 and whatnot. I am going to leave a few exercises for you. Another exercise which is again rather easy is to show that whenever set f is closed in y, then f inverse f is closed in x. So you can characterize continuity completely using closed sets also. A mapping is continuous if and only if it pulls back open sets to open sets. Equivalently, it is continuous only when it pulls back closed sets to closed sets. Okay, so this theorem sort of characterizes continuity completely in terms of open sets. Now, one important class of continuous functions that will be very useful in our study of metric spaces, and more importantly in future study of functional analysis, are linear mappings. And it's very easy to characterize linear mappings whether they're continuous or not. Theorem, let E and F be normed vector spaces. Let L from E to F be a linear map. Now the temptation is to automatically conclude that L is going to be continuous, but that's not true. Solve the exercises to see an explicit example where you can have a linear mapping between normed vector spaces which that is not continuous. Now thankfully it is true that whenever E and F are both finite dimensional, it is always true that L is going to be continuous just because it's linear. In fact, you don't even require the finite dimensionality of F. That is again going to be left as an exercise for you to analyze what happens in the finite dimensional case. But in the infinite dimensional case, just linearity does not guarantee that L is going to be continuous. However, the condition for L being continuous is rather simple. Then L is continuous if and only if there exists C greater than 0 such that norm L of x is less than or equal to C times norm x. Again, I am committing an abuse of notation by using the same notation for the norm in both the domain as well as the codomain. This is a common abuse of notation. If otherwise, if you are not satisfied with this, you can put a subscript. If you want, you can put a subscript E here and the subscript F here and a subscript E here if you want, but that is just too much notational overburden. So proof. The proof is not at all difficult. Suppose you have norm Lx is less than or equal to C times norm x. Then L is in fact Lipschitz, not just continuous, it's going to be Lipschitz. How do you see that? Because norm L of x minus L of y is going to be equal to norm L x minus y by linearity, which is going to be less than or equal to C times norm x minus y. If you recall, in some earlier chapter we had briefly studied Lipschitz functions. This shows that L is Lipschitz and therefore it's continuous. On the other hand, if L is continuous, we can of course find delta greater than 0 such that the closed ball of radius delta centered at 0 is going to be fully contained in B01. That is, you take the open unit ball in the codomain Y, you can find a delta such that L maps the closed unit ball B of 0 delta closure inside B01. I want you to think about why this is true. Again, let me tell you, this is not at all hard. If you have understood the equivalent characterizations of continuity, this should be a less than 30 seconds argument why this is true. Okay, this means if x is in E and x is not 0, then if you take L of x, this I can write as norm x by delta L of delta by norm x. Okay, again I'm just using linearity. I am multiplying by norm x by delta and multiplying x by delta by norm x inside L. Okay, and this delta x by norm x is going to be an element of this B0 delta closure. Okay, because of that this is going to be contained in B01. In other words, norm of Lx is equal to norm x by delta times norm of L of delta norm x delta by norm x, which is going to be less than 1, right? So I can write this whole thing is less than or equal to 1. This just follows because this quantity delta L of delta by norm x is there here. This whole thing, this image is there in this. So the norm of that is less than or equal to 1. Okay. In other words, if we set C to be equal to 1 by delta, we get norm Lx is less than or equal to C times norm x as required. Okay, again this proof was not complicated at all. So there is an easy way to characterize linear mappings that are continuous between normed vector spaces. Now I'm going to make a remark that would at the outset seem rather silly, but it needs to be made, especially when you're going to study functional analysis in the future. Normed vector spaces, when you have linear mappings that are continuous between normed vector spaces, so continuous linear maps between normed vector spaces are called bounded linear maps. Okay, now they are called bounded because we have this inequality. Okay, Now, you're all familiar with what a bounded function is. That just means that the range of that function has a positive but finite diameter, right? That is the usual notion of boundedness. Now, you can check that if this linear map between any two vector spaces, any two normed vector spaces, that's not identically 0, can never be bounded if you want the diameter of the range to be a positive finite quantity. That can never happen at all. So this notion of bounded, when you use this terminology bounded, this applies only to linear maps between normed vector spaces. So whenever you see this, don't make the mistake of thinking it's bounded in the usual sense. So this is actually a bad terminology. We could have just used continuous linear maps and be done with it. But for whatever reason, these maps are also called bounded linear maps, and we have to live with this terminology. If there was no existing notion of bounded, then this property is a nice way to say that the map is bounded. Unfortunately, there are two different notions of bounded now, and you have to make sure that you understand what notion of bounded is being meant in that given situation. It's not too hard actually to guess, because whenever you are in the situation of linear maps between non-vector spaces, people usually mean the notion that norm L of x is less than or equal to c times norm x. So let me make a definition. Let LEF denote the collection of all bounded linear maps between the normed vector spaces E and F. Okay, I'm going to violate my own thing that saying continuous is better. I'm going to follow the norm, no pun intended, of calling continuous linear maps bounded. Okay, so we consider the collection. Define for L in LEF the operator norm norm L is by definition infimum of c greater than 0 such that norm Lx is less than or equal to c times norm x for all x in E. Okay, you look at the collection of all c's such that norm Lx is less than or equal to c norm x for all x in E. We know that there is at least one because this L is a bounded linear map. Look at the least possible one, the infimum, and that is defined as the operator norm of L. Now that this is a norm is a check for you to do. That's rather easy to do. So let me leave it as an exercise. Show that the operator norm is a norm. It's rather easy to show. Okay, and in the exercises I am in the notes, there are several other formulas I am giving you to check for the operator norm. This is not the only way to find out what the operator norm is. There are several other ways. Please solve that exercise. That will give you an idea about this operator norm. Now let me make one more remark why this is called the operator norm. Usually linear maps from a vector space to itself is often called an operator, especially in the context of normed vector spaces. If you have a bounded linear self map, it's often called an operator, and this is the norm that you put on the space of operators. Many authors also call linear mappings between two different norm vector spaces also as operators. So for the sake of not having too many notations, this is just called the operator norm. So this was a brief study of continuity in the context of metric spaces and normed vector spaces. Please do solve the exercises. There are some interesting ones. This is a course on real analysis, and you have just watched the video on continuity.